Okay, good evening to all. The slide is visible.
Yes, sir. Visible, sir.
Okay. So today we will discuss the different contrast enhancement, image filtering, and band ratioing. These are the different techniques of the remote sensing technology. So we'll go through one by one. So the first is the contrast enhancement. So in the satellite image, like in black and white or a different multispectral satellite image, there are various contrast are there. Contrast means there is the pixel value of different object at the same wavelength. For blue or green or red, particular wavelength. So there is a difference in the pixel values. So these are called as the contrast, and it is defined as the ratio of maximum intensity to the minimum intensity of our image. So it is basically one of the ratio, that is L max by L min. So maximum intensity, L is the intensity. So maximum intensity to minimum intensity, that is the ratio. So in this satellite image, in the left side, that is the uh, left side is not clearly visible. After enhancing the contrast by different technology, then it is visible clearly. So contrast is very much important for different applications. And the right side is one of the satellite image, that is of normal contrast, and then low contrast, and then high contrast. So some of the time the high contrast also important, because sometimes satellite images are not visible clearly, but in the high contrast we have some information, so we get information of different linear features. That's why some high contrast image are also required. So this is related to the contrast enhancement. So there are various contrast enhancement techniques are there. So first of all, we will discuss the linear contrast enhancement. So there are two type of contrast enhancement. There is linear contrast enhancement, and another is non-linear contrast enhancement. So in linear contrast enhancement, there are three type of enhancement techniques are there, like minimum maximum contrast traits, percentage linear and standard deviation contrast traits, and piecewise linear contrast traits. So before going to this, we will discuss what is the linear contrast enhancements. So linear contrast enhancement is the when pixel value of an image are uniformly stretched across a larger display range by expanding the range of original input value of the image, and the total dynamic range of display device can be utilized. And this can result in certain feature being enhanced, while other features which may be of greater importance will not be sufficiently enhanced. So this is one of the drawback. So all uh, pixel information are not enhanced equivalently. So this is one of the picture. Suppose the minimum pixel value is 60 and the maximum pixel value is 158. Then if it is enhanced, then it is enhanced from minimum 60 to 0. So basically in the 8-bit computer system or 8-bit image, the value is from 0 to 255. So 8-bit means 2 to power 8. So 2 to power 8 is 256. So why it is 255? Because it includes the 0. That's why 255 plus 0 is 256. So basically the value are in the 8-bit, it is from 0 to 255. That means all the satellite image reflectance values are arranged from 0 to 255. So what What do you mean by the zero or near to the zero? So zero means the reflectance value is very low. That means it absorb more. So when one pixel absorb more, it look like dark features. So when the dark features are there, then their value is near to zero. And when it gradually increases to the gray level, then more increases to the totally brightness, so it looks like white in the pixel, then its value is gradually increases, and the value maximum increases up to 255 number. The value is maximum 255. So when one can say that if one pixel value is 10 and another pixel value is 220, so which pixel value is brighter and darker? So you generally know that the pixel value of 10 is look like the dark or black pixel, and 210 or 212 value of the pixel is brighter tone. So this the dark to brighter and dark image to brighter white is arranged in the gray value from 0 to 55. So more is the number of the reflectance value, more is the more the image is tends going towards the brighter one. So this is the scale. So when our pixel values are 60 to 155, suppose in a satellite image, so the very large bright informations are not there and very dark information are not there. So 60 to 155 is there. So when 60 to 155 is there, then suppose we want some information which are not clear in the image, so we have to enhance this value from 60 to lower value is 0, and in the right side is 158, so it extend to 255. So total range is spread from 60 from 0 to 255. So all the informations, some of the informations uh, are recorded, and if some informations are not seen in the image, so it can be seen. But the demerit is in this problem, that's when some larger value of a particular reflectance, suppose 155 or the darker tone areas, so if it is spread, then it also get lost the original value. So this is one of the problem. So for visibilities, easy to visibilities to the satellite image, sometimes we expand the value and the trace the values, and this is in the linear ways, that is left right and left way and right way. So it is trace, so it is called as linear contrast enhancement. So there are three type of linear contrast enhancement. A lot of techniques are there. So mostly in remote sensing, we use these three type of linear enhancement in the contrast enhancement. That is minimum maximum contrast stage, percentage linear, and piecewise linear contrast. So first we just go through the minimum maximum contrast trace. So in this technique, the original minimum and maximum value of the image are assigned to a newly specified set of values based on the full range of available brightness value of that image. If, and the maximum value in the original image is 155 and minimum value is 60. So this is one of the example of the minimum and maximum contrast stage. So this is minimum to maximum. Okay. So these are some of the example. This is on enhanced satellite image in A. Then stage to minimum and maximum enhancement, and stage to 90% minimum enhancement. So when we generally get the raw image, then some of the time we seen that this is the raw image. So there is no information are seen in these areas. That's why we have to enhance these areas. So after enhancing, this type of satellite image are seen. So this is also like in the different image also we can find. So during our enhancement, what is the pixel values arrangements or changes in the histogram? We will just see. So this is the pixel value are concentrated in the particular dimensions. After enhancing this, so this pixel value are just arranged in a different average ways. So this peak values of these pixels is converted in to this peak value. So peak value informations are gradually decreases, and we lost some of the informations, but overall the information of the images is um, distributed in larger ways. So this is the minimum and maximum enhancement. Okay, then percentage linear and standard deviation contrast rates. So second is the standard deviation based contrast rates. So in this contrast rates, the technique uses precise minimum and maximum value that we position in a certain percentage of pixel from the mean of the histogram. So this is the formula, that is input minus L minimum divided by L maximum minus L minimum into dn, that is digital number, maximum digital number value minus minimum digital number plus digital number minimum. So previously we saw that this is the 158, that is the digital number. Then so it is based on the percentage of change in the pixel number. Suppose 2% of dark pixel and 2% of bright pixel are there, and suppose 2% dark threshold, that is DN digital number 30, and 90% bright threshold is DN 200, and stretch is DN 30 to 0, and DN 200, that is tends to 255. So value between 30 becomes 0, and value become above 200 becomes 255. So this is the result from this is the original image, and this is the stretch image. Then piecewise linear contrast stretch. So in this contrast stretching, the multiple linear segments, instead of applying a single linear transformation, is applied. Like suppose there are three type of range is there. So from 60, minimum 60 and maximum 200 pixel. So we have to categorize this in this range into three categories: 60 to 100 one category, then 100 to 150 is one category, then 150 to 200 is one category. So after categorize all these three segments, then we have to stretch different ways. So this is called piecewise linear contrast arrangement. So in this there are segmentations are there. So before two contrasted, there is not a segmentation is applied. So this is the table. So input range is 0 to 80 is a one of the segment. Then output range is 0 to 60. Then input 80 to 160 is then resulted is 60 to 200. So 160 to 255 is transfer into 200 to 255. So when 0 to 80 value of the pixels are converted into 0 to 60, then it looks like the compressed dark tone, because 0 to 80 value is uh, compressed to less than the pixel number, that is 0 to 60. So which value is nearer to 0, so it looks like the darker tone. So here it is 0 to 80, then it is 0 to 60, so it reduces 20 value, so that is look like some not a darker tone, not a brighter tone. Then 160 to 255, so it is converted to 200 to 255. That means whose value is nearer to 255 is very brighter, so gradually brighter. So before the input range, it is 160 is the minimum, then on the output, that is minimum is 200, so it looks like slightly brighter tones. So these are this way this are categorized. So minimum 3 or minimum maximum 7 or 8 type of range also created, segments are created for particular specific region enhancement. So this is the one of the example. So in this graph, this is one of the segment of the pixels from 60 to 0 to 80, then 0 to 160 to 200, then 255. So these are the segments, and this original image to transformation into piecewise linear stretch. So this is the result of the image. So this is also one of the example. So in the histogram, the original pixel values are in a linear ways. Then after categorize or after segmenting all these, there are three segments are seen. This is one of the segment, 0 to 50 or 60, and then 60 to 200. Near 200 is one of the segment, which is lower than the first segment. Then 200 to 250, this is one of the segment. So it is higher values as compared to the middle values. So this shows that there is a segmentation is applied, but before this there is no segmentation is present. So this is the original image, and this is the piecewise linear stress. So piecewise linear stress is based on the different segments stretching. Then another method is non-linear contrast enhancement. So basically in the linear enhancement, there is a linear way of enhancement. These techniques are used, but in non-linear enhancement, there is no linear enhancement techniques are used. So the output pixel value is not a straight line or any linear ways. So in the linear contrast is the relationship between the input and output is given by a straight line, that is y is equal to mx plus c. So it is a regressional and relationships. Then in nonlinear, there's a transformation curve is different rays of DNA are enhanced differently. So different reflectance values are enhancing differently depending on the function used. So which type of functions are used is based on the different areas calculated. So what is the purpose of this enhancement of the nonlinear and contrast enhancement? So it is enhanced detail in specific brightness range. So some specific brightness, if there is a high brightness are occurred in the some areas, then it can be reduced by different techniques are used. So without exposing and on under exposing the rest. So specifically, particular area are enhanced. So there is not a uniform enhancement of the all the image, so that the rest of the pixel informations um, are in the constant values. So it is useful for image where important details are concentrated in certain DN ranges. If certain DN ranges values are not accurately reflect in the image due to the some low enhanced image, so this can be enhanced uh, particularly for particular areas, so that it is clearly visible and it is very much helpful for analysis this satellite image. So some of the common nonlinear contrast enhancement techniques are like histogram equalization. So mostly all of you know about the histogram equalizations. Then Gaussian contrast traits, then logarithm traits. So there are a lot of nonlinear and contrast enhancements are there. So mostly we use these three type of contrast enhancement. So first is the histogram equalizations. So in the histogram equalization, there's a redistribute pixel values so that all brightness level have roughly equal frequency in the histogram. So basically, when the arrangement of the pixel is there, so it is redistributed and the roughly the equal frequencies are there, and it spread out the most frequent intensity values, and it maximizes the global contrast and especially in the low contrast image. So it is one of the example, that is picture A is very low contrast, then after histogram equalizations the image is clearly visible. So when the graph will show the different pixel arrangements, so this is the original arrangement of the pixel in the picture A. Then when the histogram equalization techniques are applied, then all these pixels are arranged from lower to higher values, so that this looks like this. So this is roughly the equal distribution of the frequencies and distribution of the reflectance values from this 0 to 255 range. This is the reflectance range in the 8-bit system. So when we stretch it from minimum range value to maximum range values, then some of the image give the good results, but it is not correct for the all the images. Then same is the right side image. So this is the contrast of slight contrast. Then when we contrast largely for the large values, then it look like this. Then this is one of the contrast. So different contrast techniques are used to give the best results. So this is about the histogram equalizations. So this is one of the satellite image. So after histogram equalization, it looks like this. So this is the urban areas, settlement areas in the middle part. Then it is slightly brighter than the previous one. Then Gaussian contrast trace, the second method of the nonlinear contrast stretch. So it is performed in the similar manner as you operate the histogram equalization, and it is generally enhance the middle intensity range while suppressing the extreme. So it is generally enhance the middle intensity range from 80 to 150 range of the pixel informations are there, and it is also called as the Bell curve. The Gaussian normal distribution is also called as Bell curve. So the curve is defined by its mean, that is mu, and the standard deviation, that is sigma. The mean determines the center of the curve. So this is the center of the curve, and the standard deviation control its width. In this context, the Gaussian curve represents the ideal distribution of the pixel intensity for well-balanced image. So this is look like the bell curve. So generally, it emphasizes in the middle part of these areas. So this 68% of these pixel informations are emphasized morely. So after that, you just get the uh, result of this enhancement. So the right side image is one of the synthetic aperture radar image, and when it is enhanced in Gaussian normal distributions, so it looks like this. Then logarithm stretch. So this is the last nonlinear transformation. So it is generally used for the image with a narrow range of dark pixels. So some of the narrow range are used, and it is expand the dark area while compressing the bright areas. So when some dark areas are high values, so it is enhanced to get the less dark areas, and same at the same times when the lighter brightness area is very large, then it is compressed this lighter areas. So to equalize the image reflectance to give the good result. So logarithm approach takes DN values in darker part of the histogram, and it also uh, stretches the DN values in brighter part also. And many satellite images a larger portion of pixel values concentrated in the low end of the brightness range. For example, water bodies. So we have already discussed that generally the water bodies and dense vegetation and evergreen vegetations like mangroves and other areas, and some of the shadows and mm, some of the wetland areas gives the darker tones. So some of the times if it is very dark, then inside these areas there is no other features are not found. So that's why some, if the darker is very uh, concentrated in particular area, then it is just enhanced in logarithmic stage methods. And what is the advantages of this? So it is basically highlight the shadow water bodies and low reflectance objects. So which features are very low reflectance, then it also gives the good results. Then useful for nighttime images. So some of the nighttime images and thermal imagery like Landsat TM data, where values are clustered at the low end. So this is one of the graph. So how the logarithmic stretch is there, and this is the linear stretch. So this is about the uh, contrast stretch, about the linear stretching and non-linear stretching. After that, we will discuss the image filtering and band racing. So before going to the band racing, so we have to discuss some image filtering techniques are there. So basically, the image filtering is the technique of enhancing and suppressing the tonal changes in the image. Just like different filter are used physically or different in the different applications. So that basically we just filter some of the part which is not required for us. So we just filter the required part to be concentrated in the as our output, and some of the debris or some of the unwanted parts are retained in the filter techniques. So likewise in the remote sensing, the uh, information like the frequencies of the EMR radiations are filters. So it is a electromagnetic radiation based filters are there. So there is a non-physical filtering. So in this, the best is based upon the frequencies. So different frequencies are filters, and different reflectance values of the pixel are filters. So different kernel are used, just like some square filters are there. So this is kernel is one of the metrics, because all the satellite image are in the matrix form in XY coordinate, and kernel are also this is a small matrix form, and they have some values are there. So when some filtering is applied, so these kernel values are multiplied with this original uh, image pixels. So after the getting the results, so this uh, filtering technique is finalized. So first of all, we just take, there are two type of filtering is there. There is a spatial filtering, and what is this? Second is frequency filtering. So first, the spatial filtering. Spatial filtering is an image processing technique where pixel values are modified based on the value of surrounding pixels. So if some of the pixels of a particular area is not correct, or randomly get the reflected values, which is not accurate, then this 2 3 pixels are corrected with the averaging all the surrounding pixels, and for this the special filtering is used. Suppose we have a water bodies, so most of the water bodies are looks like the dark tone in the satellite image. So suppose 1 2 3 pixels are giving the brighter tone in the water bodies. So it is a error in the pixels. So the surrounding dark pixels are calculated. The average of the dark pixel calculated. Then this is applied to the uh, error pixels informations. That's why this special filtering is applied. So each pixel in the output image is computed taking weighted average of neighboring input image, and weight are defined by the filter kernel. Kernel is just like 3 to 3 into 3 matrix or 5 into 5 metric form matrix form. And this kernel move over the image by image in pixel by pixel, that is called convolutions, and then new pixel values are computed. So there are three type of special filtering techniques, that is low pass filter, which give the smoothing effect to the satellite image, then high pass filter, that is sharpening the images, and then band pass filter, so it is band based, spectral band based. So this is the low pass filtering technique, that is smoothing. So what is the purpose for the low pass filter? To reduce the noise and the blur of the image, then remove the fine details. And how this is happening? So averaging the nearby pixel to repeat brightness and changes to minimize this. So some of the example of the kernel is, that is the kernel. So in this right of the images, that is, and there is different reflectance value of the subtle pixels are there. So this is in a different matrix form. So one of the pixel information is 84, 85, 78, 62. So one kernel is, one of the kernel of the our filter is 11111. So every pixel is the information of 111. So what we do, so we just multiply this kernel information just to these areas, so which is give some error. So then the final result is, so it is calculated in this ways, like 84 into 1 plus 85 into 1. So this way all these metrics are multiplied, and then divided by 9. So it is a 3 into 3, then that means there is a 9 pixels are there. So after averaging all this, it is the 73. So likewise, some values are there. So likewise, different values are um, converted to the different ways after using the kernels. So they give the different resultant uh, image pixel informations. So after that, suppose this is the image, then after that the resultant images look like this. So this is like the low pulse filter. So it just give this smoothing effect of the satellite image. So generally some of the application is cloud removal, noise suppression. If there is a noise in the satellite image, then it is also recalculated. So generally, the low pass filter is typically help to improve the appearance of the image. So if the appearance of the image is not good, then low pass filter is applied to give the good appearance of the satellite image. So this is one of the convolution matrix of low pass filter. Suppose this is the kernel, that is 1 into 1 into 1. So this is applied to this type of pixels. So then 24 to 29. So these 3 by 3 areas. So this is the areas, the black dark space is there. Then when applied to this, then the different resultant values are there. Like the 24 is converted to 26, and 27 is converted to 26. So this is the resultant pixel information. Then this is the resultant satellite image. So the upper one is the original image, then lower one is the filtered image. So this is one of the example in the low pass filtering. When the low pass filter is applied, this is the resultant of the low pass filter. So some of the brightness values are largely affected, and it is get the largely brighter tone. Then high pass filter. So high pass filter keeps the high frequency component while filtering out the low frequency one. It is used to make the image sharper. So it gets the sharper image. And for high pass filter, the kernel typically have a positive value in center and the negative value in side. So this is the example of the high pass filter kernel, that is the matrix 3 into 3. So in this, the middle part is the positive value and all the surrounding parts is negative value. This is also one of the negative value. So this 3 into 3 pixel is uh, continuously applied to the whole pixel of the images. Then it is calculated in the matrix form, the different pixels values. Then the resultant values are given the different output. So kernel is used for the different filters. When the kernel is applied, the central part value is multiplied by 5 by 9. So this is the process, and this is the resultant. We use the high. So some of the missing road and some of the other lines are not seen in this left image. But after sharpening this, all the road networks are mm, clearly visible. But other features are uh, losses their informations. So for different edges finding, and for different boundary water and land boundary estimations, then this high pass filters are used. So this is all the application is boundary detection and highlighting the road and rivers. For particular for this purpose it is used, and for land use land cover or supervised classification is not used, because it give a lot of information. Uh, Generally, the high pass filter kernels, the middle value is positive, and all the surrounding values are in the negative. So this is there are the six kernels of the high pass filters are given in this table. So this is one of the example of the high pass filter. So this is the original image. After applying the filter, this is the image look like. So only edges and boundaries are only uh, shown, and rest of the information are lost. Then band pass filter. So band pass filter in remote sensing is a spatial filter that passes features within a certain spatial frequency range while suppressing both low and high frequencies. So mm, this is also called as the medium spatial frequency filter, because it is combine of the high pass filter and low pass filter. So it is not a low pass filter or not as a high pass filter. So that's why it is called as band pass filter. So this is the image of the band pass filter. It's the left side A image. Then the low pass filter B. Then the high pass filter is C. So the graph are shown. There is the high pass, then low pass, then band pass. So what is the application in the band pass filter? So a lot of applications are there in the band pass filter. like detecting the lineaments and faults of the certain scales. So lineaments in the geological term is a linear surface underground, the rock structure is there, and faults in the certain scale is there. So this can be found with the help of bandpass filter. Then urban studies like identifying medium-sized built-up patterns, and for vegetation mapping like isolated mid-scale canopy textures are there. Then in the oceanography, there is a detecting wave pattern while suppressing the background water tone and small scale ripples are there. So in this way, in the geological field and urban studies and vegetation mapping and oceanography, a lot of use are there. You know, and basically your third band or fourth band to get the different outputs. So of different band ratios. So these are the select images of different band ratios with the ratio of the pixel to the band 4, 5, 6, or any requirement is needed. So generally the pixel topography mix are used for NDVI calculation, NDBI calculation, then NDWI calculations. Different indices are there. So in this indices form, there is a band 3, one spectral bands, and band 2, this is the band 2. These are the reflectance value of the each pixels. And the second, another band, that is band 2, have different spectral reflectance values like 2, 16, 8, 812, because in particular same area, if we taken into account bands have different reflectance values. Suppose for in infrared spectral reflectance in the vegetation areas, but as compared to this in the blue band, it is low reflectance. So these are the values for different bands. The value is different. That's why if the value is different, so we just showing the ratio the value of this band's information to get the different result. So we have just band 3 and we have just to ratio the band 3 to band 2. So after that the 10 is divided by 2, the same position is divided, then it is resulted into 5, then 16 is divided by 16, then the result is, well, it is 1, and the last pixel the value is 9, and from them are this below. So for near infrared plus red, so this is one of the technique. And differentiation water index is there, then atmospheric correction to reduce lighting effect, also band reduction techniques are used. So nowadays NDVI, NDBI, and NDWI, so ND, uh, uh, so SAVI, so a lot of indexes are used. So all these indexes are based on the band restoring techniques. Some of them give the good results and different pixels, and some are not up to the requirement of this result. Yeah, in the previous class and today's class. So we'll just discuss all these questions. Maybe ask in the exam, discuss this. So which of the following is the example of spatial domain image enhancement? So out of these four, like histogram equalization, Fourier transformation filtering, radiometric correction, and atmospheric correction, which is the image enhancement technique? So out of this, histogram equalization is the right answer. So it is actually just then the main objective of image enhancement is, so what is the objective of the image enhancement? To reduce the file size. It is not the objective. Improve the visual appearance of the image and convert raster to vector or perform classification. So it is not related to the classification technique. So B is the right answer. That is improve the visual appearance of the image. So for the enhancement technique is basically for the visual appearance, not for other purpose. In the contrast stretching, the original digital number are compressed into smaller range, expand to cover the full display, or randomly distributed or convert to frequency domain. So it is generally the contrast stretching is generally expand to cover the full display range. This is the one of the objective. So it is B is right. Then four, that is which image enhancement technique improve the visibilities of dark feature by increasing their brightness and disproportionately. So visibility of dark feature by increasing their brightness. So this is the logarithm contrast stage, not the linear or possessive or Gaussian stage. So this is A is the right answer. So question number five is in remote sensing, spatial filtering is mainly used for. Spatial filtering is mainly used for removing geometric distortion is not correct. So it is not related to geometric distortion. Emphasizing and suppressing specific spatial frequencies or compressing image data. So it is not related to the compressing image data. Changing image color is not one of the objective. So C is the answer. Emphasizing or suppressing spatial frequencies. So generally filtering is related to the frequencies. So if any frequency related question, so this is the filtering. Then high pass filter are mainly used to smooth the image, so reduce the noise, enhance edges and fine details, or reduce high frequency component. So generally we just discuss that smoothing of the image is based on the low pass filter. So low pass filter gives the smoothing image, and noise removal is not related to this. So enhance the edges and fine details. So this can be enhanced by edges so that we can take the different boundary information. Then Gaussian contrast stage is mainly applied to. So Gaussian is the mesh histogram to Bell's curve. That is the B answer. Then in piecewise linear contrast stretching, the histogram is equalized in one single step, divided into multiple segments for separate stretching, compressed into low value, and converted into binary. So piecewise linear contrast is generally it can create different segments, 3 segment, 5 segment, or 10 segments. So based on this segment, it can enhance the image. So B is the one of the answer. That is, it is divided into multiple segments for separating states. So this is the answer. Then low pass filter in spatial enhancement is mainly used for enhancing sharp boundaries. So sharp boundaries based on the high pass filter. Increasing contrast rate is also the high pass filter. Stretching pixel values or noise reduction and image smoothing. So image smoothing is the answer and noise reductions. So this is the A is the answer. Then number nine, which of the following best describe the purpose of band racing in remote sensing? Band racing. So band racing can reduce atmospheric and illumination effects. This is the answer. So just reduce the atmospheric and illumination effect. It is not like the to merge thermal and optical data to enhance the panchromatic image, not like that. Only the atmospheric and illumination and topographic effects are related to this band racing. In band racing, the ratio is calculated by adding two bands together or dividing pixel value of one band by another or multiplying or subtracting. So it is based on the dividing the pixel value of one band by another. Then NDVI normalized difference built-up index is there. Then NDVI normalized difference vegetation index. Then normalized difference water index. So NDVI is vegetation is like normalized differential vegetation index. and other are for water, that is NDWI. For soil related index, that is SAVI, SAVI, and for built up index, that is NDVI. So rest out of this, a lot of in NDVI different indexes are there. You have to complete this season by all this, completing this and question answer. So if any doubt is there, then you can ask. Sakshi Sudhakar. Okay, so कुछ डाउट है क्या? अगर कुछ
सॉरी सर,
डाउट
वो
नहीं है
बाय
तो देन
सॉरी सॉरी सर, वो बाय मिस्टेक हुआ, सॉरी।
ओके ओके. गोकुल राहुल, ये कुछ डाउट है? सो सबको रिक्वेस्ट है एक कि आप ये बुक्स थोड़ा सा पढ़ लीजिए, बिकॉज a lot of informations are there in the given books, in the IGNOU books. So all these are very much important topics for going to the remote sensing and image analysis fields. So this contrast stretching and all these digital image processing techniques are the basics for the image analysis in the future. So the statistical analysis, then digital image processing analysis are very much important in near future, and in the machine learning techniques also we use this type of basic informations, and then this geospatial statistical analysis, all these are very much helpful. Okay, then we'll the next class will be,
On
I think
18th,
in
sir. 18th.
Monday. 18.
Mm, 18th.
So
Mm.
tomorrow there is no class, and
Okay.
after, so up to Sunday there is no class. Okay, then we'll meet in 18. Thank you. Good night.
Thank you, sir. Thank you, sir.
Thank you.